All right, so we've covered a lot of the basics of statistical thermodynamics now, but there's one major topic that we haven't covered, and unfortunately in your book, this major topic isn't really dealt with until chapter 15. So the material I'm going to talk about here is kind of ahead of where we are officially in the book. But it's important enough that I think it's good to introduce it here so we can use it as we're going through some of the applications that are the next major topic. We saw earlier when we were talking about isolated systems that if you can calculate this quantity W, the number of microstates that are available to the system, for an isolated system, then you can also calculate entropy for the system. And entropy gives you everything else, all the thermodynamic properties, all the questions about driving forces, all the questions about when you're at equilibrium and when you're not. All those things can be obtained from entropy and therefore from W. So W contains all the thermodynamic information that you want. But now we have an open system. It's not an isolated system. Is there an equivalent kind of quantity to W for an open system? And it turns out there is. I'm going to show that or prove that way at the end of this little lecture, but I'm just going to give the result for now. We'll talk about that, then we'll prove it later. The analog to W for an open system, a system that's open to a temperature bath, remember, not open in every way, but open to a temperature bath only, is this quantity Q, the canonical partition function. And we've seen already above that the canonical partition function, or really the log of the canonical partition function, is related to the thermodynamic energy, the mean energy, and also the heat capacity. And now we see that this canonical partition function, if we take the log of it, is proportional to the Helmholtz free energy. And remember that for a system in contact with a T-bath, an open system in contact with a T-bath, changes in the Helmholtz free energy are proportional to changes in the total entropy of the universe. In other words, the second law basically turns into changes in Helmholtz free energy and is most readily or most conveniently expressed in terms of Helmholtz free energy rather than total entropy. And now we see that Helmholtz free energy, which basically gives the second law for open systems, is also basically the same thing as the logarithm of this quantity Q, the canonical partition function. And though I haven't said this before, well, I have said it before, but not for a while, all of the thermodynamic properties of an open system can be found if you know this quantity, the Helmholtz free energy, as a function of temperature, volume, and mole numbers. And the canonical partition function is a function of temperature, volume, and mole numbers. So if we know Q, we just got to take the log, multiply by temperature, and we can get the Helmholtz free energy as a function of temperature, volume, and mole numbers, and that will give us everything else. So this relationship, which is now kind of messy here, let me get rid of all this stuff. This relationship right here that I put in a box is the equivalent for an open system to our earlier relationship between entropy and W for an isolated system, and therefore it's the focus of an awful lot of thermodynamic attention, statistical mechanics attention. When people are doing statistical mechanics, usually what they're focused on doing is calculating this Q, which is easy if you only have a few states in your system, if it's a really simple system. But if it's a more complicated system, then calculating Q is a non-trivial thing, and we'll see examples of that as we go along. Okay, so this section is going to talk a little bit more about this quantity Q and its importance. First of all, notice this is just kind of adding to or elaborating on what I said already, that for an open system, changes in Helmholtz free energy are proportional to changes in total entropy, and therefore when the Helmholtz free energy goes down, decreases, that's the condition for a spontaneous forward process. When the Helmholtz free energy is equal to 0, that's the condition for equilibrium, and when the Helmholtz free energy is greater than 0, that's the condition for a spontaneous backward process. And all those conditions line up to the equivalent conditions that exist for an isolated system. Notice also the sort of formal mathematical similarity between the relationship of Helmholtz free energy to Q and the relationship of entropy to W. They're both obviously playing the same kind of role, changing what must be changed for the fact that one's dealing with an open system and the other one's dealing with an isolated system. That suggests that since W is counting the number of microstates available to an isolated system, then in some sense, Q must be counting microstates for an open system. And that's true, but it's true only in a sort of slightly indirect way. And so let's see how that works. First of all, yes, if you want to sort of make analogies, W is to Q for an isolated system. W for an isolated system is the same thing, effectively, as Q for an open system. And again, let's just remind ourselves of what Q is. You take these Boltzmann factors, e to the minus beta, for each energy in the system itself. You sum over all those guys, and that's Q. And it's not obvious at all to begin with that this quantity, this sum, should be the quantity we're after. So let's see in what sense that's true. To do that, all right, this is saying some of the things I already said up above. Let's look at Q a little bit harder. Earlier, when we were deriving the Boltzmann distribution in general, we showed that the total number of microstates available to both system and surroundings, so here's cis and here's sur, and the total number of microstates available to both of them at once is equal to the number of microstates available to the surroundings alone times the number of microstates available to the system, and then summed over all the energies that can exist inside the system, and therefore all the energies that can exist within that range of energies in the surroundings as well. We also saw in that same section that the number of microstates available to the surroundings can be written this way. If this is a T-bath, and if it's strictly speaking a T-bath, then the number of microstates available to the surroundings is this exponential quantity with the total energy of both system and surroundings up in the exponential times this Boltzmann factor, which has the energy of the system divided by kT, or that's e to the minus beta E as well, since beta is equal to 1 over kT. So if we put this expression here up into there, then we get the following. First of all, we can factor out this guy because it doesn't depend on the energy of the system, which is what we're summing over here. And what's left here is just Q. If you recognize it, it's just Q. And so we have that the total number of microstates available to the full system, both surroundings and a little system, is proportional to this canonical partition function, Q, and the proportionality factor is a constant, right? The total energy of both system and surroundings is the total entropy of the universe. That can't change. and the temperature, which also can't change if the surroundings is acting like a tea bath. So a lot of things follow from the fact that the surroundings acts like a tea bath, but any surroundings that's large enough will act like a tea bath. So that's no great assumption or restriction on our part. So this is just a constant, and what we're saying, therefore, is that the number of states available to the full system is proportional to the canonical partition function by means of a constant, and we don't ever really even need to know that constant. Knowing that these two guys are proportional to each other, the canonical partition function is proportional to the total number of microstates available, that's enough. And so here's that relationship just written out by itself, because it's an important one. All right, so let's look at Q then with an eye towards understanding in what way that actually works. So first, let's point out this quantity e to the minus e sub I over kt that appears in Q, right? Q is the sum over all the microstates of the system, e to the minus beta e sub I. And that's, that is that. So we're summing over all these guys, but remember where these guys came from. They came from W sur up here, right? So I've made a mess out of this, but let me erase some of that stuff, make it clearer. This right here, which is part of W sur, is where that Boltzmann factor came from originally. Those Boltzmann factors come from the surroundings. They're not a property, really, of the system. They're a property of the surroundings, or they're keeping track of the number of microstates in the surroundings. So Q, then, is just adding up all the little Boltzmann terms, each of which is just the effective number of microstates that are available to the full system, given that it might have cost some energy to create that state within the system itself, and therefore might have decreased the number of states available to the surroundings. So the reason this Boltzmann factor out here for a high energy level is smaller than maybe the Boltzmann factor for a low energy level back here is because it took more energy to create that state, and therefore cost some microstates to the surroundings. All right, let's look then at an example. Let's consider a case where we have, again, a very simple system with just 4 microstates. And even simpler because I equally spaced them, so all the gaps between the 4 microstates are the same, and the gap size is just this quantity epsilon. And that means that the 4 levels of the microstates are epsilon, 2 epsilon, and 3 epsilon, and I've set the energy of the ground state to be 0 because that's also convenient. That means that for this case, the partition function, the canonical partition function, is just 1 for the ground state, e to the minus beta e for the first excited state, e to the minus 2e for the second excited state, and e to the minus 3e for the third excited state. And now I'm going to plot that Q as a function of temperature and see how it behaves. If you're at very low temperature, that means beta is large, because it's 1 over kT. And that means all these exponentials out here are basically 0. That means Q is essentially 1. What that's saying is that under those circumstances, all the population's in the ground state, and there's really only one state that's available. When you start raising the temperature, however, and you can see that these numbers down here are temperature in units of the gap size, or it's kT really, in units of the gap size. When you've reached 3 or 4 gap sizes, now you've got enough thermal energy So there's appreciable population up here. The populations in the lower states is higher than in the upper states, but there's still some appreciable population up there. And now the number of available states is approaching 3. If you keep going to higher and higher temperatures, eventually you get so much thermal energy available that all the states have roughly equal population, and therefore the number, all these exponentials become essentially 1s, and Q approaches the value of 4 asymptotically as the temperature goes to infinity. So as temperature goes to infinity, Q always approaches the number of microstates available to the system itself. And for for temperature less than infinity, the fact that Q is also less than the full number of microstates is just reflecting the fact that those upper microstates aren't populated very well. And again, Q is just accounting for the number of microstates available to the whole system. The last thing I want to talk about before we quit and begin the material from chapter 14 is this derivation of this relationship. I said we were going to skip that up above, but now let's talk about it. It's fairly short given all the results we already have, and we'll see that this is true. We'll also see that there's a close relationship between Helmholtz free energy and the total entropy of everything, system and surroundings. So we already have that the total entropy is equal to K times the logarithm of the total number of microstates. And we also have, we've seen this relationship now 3 times, that the total number of microstates is the number of microstates available to SIR times the number of microstates available to the system summed over all of the energies available to the system. We also saw, this is now the 3rd time we've seen this too, that the number of microstates available to SIR is some constant factor that depends on the total energy of the universe, of system and surroundings, times this Boltzmann factor that accounts for the energy cost of sucking some energy into the system or putting some energy out to the surroundings for that matter. And so if we plug that into there like we did up above, and then we factor this out of the sum, we get the result I just got a few minutes ago, which is that the total number of microstates available to everything is just a constant times the canonical partition function. If we then take the logarithm of that W in order to get the total entropy of system and surroundings, this first factor contributes this term to the total entropy, and the Q contributes this term to the total entropy. So the logarithm of Q is contributing, making a contribution to the total entropy. And this is just a constant. So already we have that the logarithm of Q is essentially, it's the part that changes and accounts for changes in the total entropy. This thing is just a constant, so changes in the entropy don't come from there. They all come from over here. All right. Now let's rewrite the total entropy as entropy of system plus entropy of surroundings plus entropy of system. Entropy of surroundings is just energy of surroundings divided by T, and there's the entropy of the system again. The energy of the surroundings is just the total entropy minus the entropy of the system. And then rearranging that a little bit, I get this entropy of the total entropy term. I've now grouped this over with the entropy of the system. I identified this quantity as the Helmholtz free energy, and so it turns out, when everything is rearranged, that the total entropy of everything, system and surroundings, is this constant term minus the Helmholtz free energy divided by T. So if I now multiply by minus T on both sides, then I get that down here minus T times the total entropy is just A minus this constant offset, which is just the total energy of everything and doesn't do anything. And if I now compare this relationship, so let me circle the part that matters here. Oops. Let me get rid of all this other stuff, all these distractions. And now if I take, this is equal to total entropy. If I take that and I equate it to this, then you can see that I have, well, let me just write it out. Minus A over T plus ET over T is equal to this thing, which is K log of Q plus ET over T. These guys cancel, and we have that A is equal to minus KT log of Q, which is the fundamental relationship I got above, and here it is written again. And so that proves that, in fact, the logarithm of the partition function is essentially the same thing as the Helmholtz free energy, which is the central quantity for any system that's in contact with a thermal bath. Here I'm just making the same points I made up above, namely that Helmholtz free energy, changes in Helmholtz free energy give us changes in total entropy, and that's total entropy there. Yeah, oh well, leave it that way. And that's the end for this section. The next thing we're going to do is apply all these relationships. We've got a ton of relationships. So the very top of the next section of notes summarizes all these things. So the next thing that's actually coming is a summary, which I figure everybody needs by this point. But then right after that is we're going to take all these relationships and we're going to apply them to molecules. And we're going to calculate all the statistical thermodynamic properties of molecules using all these nice relationships we've been developing all along. So all the sort of payoff for all this sort of general theory that we've been doing is coming next.